Yeah, so the title is a Surfeit of SSH Ciphersuites, and we deliberately chose the word Surfeit for the paper to make people go and look it up, right? It's a good way of getting people to pay attention to your research paper. What the hell is that about? Let me go and find out what a Surfeit is. So yeah, the dictionary definition of a Surfeit is that it means an excess of something, too much of something. And as we know, too much of anything is a bad thing, right? As we will, well, it's debatable. I can see how this hour is going to go. So the only use of the word Surfeit in the English language really is a 13th century report on the death of King Edward II, I think, or maybe the third, who is reputed to have died from eating a surfeit of lampreys. And a lamprey is like an eel. I don't know what that is in the local languages, but elan or something maybe. It's a fish that you eat. So he ate too many of these things and then he died. So a surfeit of lampreys. And actually, none of my co-authors knew this word either. None of them were native English speakers. I'm the only one. But I insisted on having this in our title. Okay, good. So that's the title. Here's what we're going to do. I'm going to introduce you to SSH. I hope that for most of you it's already a familiar thing. How many of you are actually using SSH? Ah, amazing! That's the highest percentage I've ever had in an audience. I'm in the right place.
This is the security group of
Sure. Okay. So then I'm going to talk about some of the work that we did in the past and other people did about SSH and its security. And actually the focus in this talk is all about the symmetric crypto in SSH, only the symmetric crypto. So even better to come to KU Leuven to give a talk on that aspect of SSH. You could do a very similar research paper, and maybe somebody will, about the use of things like elliptic curves or digital signatures or all of those asymmetric primitives in SSH. We're really focused on the symmetric stuff. I'm going to report what we did by measuring the internet for SSH servers. And then I'm going to show you a new attack on SSH that we found as partly as a consequence of this work. And then on the flip side of finding attacks, I'm going to show you a flavor of the security analysis that we did for the other kind of encryption modes that are available in SSH, and in particular in OpenSSH, which is one of the leading implementations of the SSH protocol. And there's a list of things there. And then we'll have some concluding remarks, and there's actually a mismatched parenthesis there. That's quite funny. That's the parenthesis that's missing from the Best Paper Award certificate that they gave us for this work at CTS this year. There was actually a parenthesis missing on the. So it's arrived finally. It's actually a mistake from this work. Okay. So introducing SSH. Here's what Wikipedia says. I think we'll skip this slide because you all know, right? Most of you are using SSH in some way. If you've never heard of it, it provides a secure communication facility. It's basically the protocol that allows system administrators to work from home. Good. I'm glad you like that. But actually, increasingly, a lot of internet-connected devices also have some kind of SSH functionality on board, like your set-top box or your TiVo or whatever probably has by now, or your home router may well have SSH functionality. It may be disabled. It may be possible to enable it, and it may even be possible to enable it remotely and log in using default passwords. Think about security there. Okay, so what we're going to focus on in the rest of this talk is this thing called the SSH Binary Packet Protocol, or BPP, and this is where the symmetric crypto magic happens. So we're going to assume that some kind of handshake protocol has run, that some symmetric keys have been established, and that we're ready to start using this crypto on the payloads. Okay, so think of this as being your login details, your username and password that you've typed at the command prompt as you're remotely logging into some server. And that's the thing that we want to cryptographically protect. And here's what SSH does. It does some encoding step on this data, on this payload data. So we have some padding here. It's always good to have padding. There's a byte that describes how long the padding is in bytes. And this padding is actually random data. So we need to have a padding length byte here to tell us how much to remove. And there's also a packet length field which describes how long this data structure is. Okay? And we're also going to incorporate some kind of sequence number into the cryptographic processing, and that's to prevent an adversary from reordering the packets or deleting certain packets from the stream of packets that we're going to have. Okay, so basically our data is cut up into these payloads, and we'll have many of these ciphertexts that I'm about to show you being sent across the network over time. So the first thing that we do is we encrypt to get a ciphertext. Typical options for the encryption algorithm here would be something like CBC mode encryption using AES, for example, or counter mode encryption, or if you don't really care about security, you can use RC4. Okay, and we have a MAC computation, and the MAC is computed over the encoded plaintext together with the sequence number to give us a MAC tag, which is then concatenated, put on the end of the ciphertext. And the MAC is implemented using something like HMAC, which you can think of as a PRF. So you can think of the bytes here as being pseudo-random bytes. Okay, and so one of the things that, well, let's come to that in 1 second. Let me just do things logically. So this is an example of an encrypt and MAC construction, because we're encrypting the plaintext, and then we're also macking the plaintext. Well, it's not quite macking the plaintext because we're also incorporating the sequence number here, and that makes the construction stateful. So every packet that's sent, every payload that gets sent, the sequence number is incremented by 1, and that sequence number is incorporated into the MAC computation. So when you're receiving packets and checking MACs, you'll be using a corresponding value of the sequence number that you hold, at the server, for example, and you'll be incrementing it by 1 for each packet. And so if the packets get out of order, the MAC will fail. And you will say, okay, something went wrong in my connection, and actually you then tear down the connection and throw away the keys. Okay, so the incorporation of the sequence number there gives us a stateful construction, which can achieve some kind of anti-replay, anti-reordering kind of capabilities. The packet length field here, you might have noticed, gets encrypted. Okay, so the first 4 bytes, which are somehow describing how long is this ciphertext, are actually encrypted as part of the encoded payload. And what this means is that if you look carefully, for a good encryption mode like CBC or counter mode, if you look at a ciphertext followed by a MAC tag, it's just going to look like a long sequence of pseudo-random bits and bytes. Okay? And in fact, if you have a sequence of these pairs going across the board here, being sent across a network, it will just look like a very long pseudo-random sequence of bytes. If you did not encrypt the length field, if the packet length field was outside and was maybe sent at the front here as some kind of metadata, then that would not be true. You could see how long the individual ciphertexts were. Okay, and so it seems to have been very important to the SSH protocol designers to make sure that as much metadata as possible got hidden, including the lengths of the packets. And you probably know why that is, because they're worried about traffic analysis attacks, where maybe the length of the ciphertext that you're sending leaks important data about the data itself. Okay, so encrypting that packet length field, though, turns out to have been a really bad decision from a security perspective. And I'll show you a little bit later on an attack that we found back in 2009 that exploits the fact that the packet length field got encrypted. Okay, so it turns out to have been a good thing to do from the point of view of trying to improve security, but actually a bad thing to do from the point of view of trying to improve security.
Okay. The sequence number isn't sent over that?
No, it's not. Thanks for pointing that out. So the sequence number is maintained at each end of the connection, and because this is all running over TCP, you can assume that that you're going to get the packets in the right order unless the adversary is trying to do something, and then the incorporation of the sequence number will detect that. Yeah. So there's no explicit sequence number. And TLS, for example, does the same thing. Okay, there's a sequence number, it's incorporated into the cryptographic processing there, but it's not an explicit part of the packets. Good. Okay, so that's what we're going to be studying for the next, 45 minutes or so, this kind of construction here, and what kind of security it gives us. Okay, so there's been quite a lot of study of the SSH BGP, not surprisingly, given that it's quite an important protocol. The first serious paper was really by Bellari, Kono, and Namprempre back in 2002, and they introduced some special new security notions to enable us to study this kind of constructions called stateful security. So they had stateful in CPA and stateful integrity. Okay, so if you're familiar with the kind of formal analysis of symmetric encryption, think of stateful versions of the notions that you already know. And they actually proved that SSH CTR was secure, and also that SSH CBC was secure. In fact, you can't prove that SSH with CBC mode, as defined here, is secure because there's actually an attack. which they also exhibited in the same paper. So there's a problem with the way that CBC mode works, which is that it uses chained initialization vectors. So you know that CBC mode needs an IV, and in SSH, what they used for the IV was the last block of the previous ciphertext. Okay, which means that the attacker, who maybe knows where the message boundaries are, has seen the IV before it gets used to carry out the next encryption. And that enables a certain class of chosen plaintext attack. If you know about TLS, you might have heard of the Beast attack. Well, the Beast attack is the same kind of attack against TLS as the Bellari-Kono-Namprempre attack was against SSH. But what they did prove was that if you don't have IV chaining, if instead you have proper random initialization vectors for each packet that you send, then you get a security proof. You get some strong security corresponding to the stateful security notion. So this is basically saying the attacker can learn nothing about the messages, he can't forge packets, and nor can he do any kind of reordering or dropping of packets without being detected. So then in 2009, this is where I first got interested in this protocol, we broke SSH in CBC mode, including for the variant that was proven secure by Bellari, Kono, and Namprempre. Okay, so something went wrong somewhere, and what our attack exploits is the fact that an attacker can deliver a ciphertext, as in this picture, one block or one byte at a time to a receiver and observe what happens as each byte or each block gets processed by that receiver. And I'll show you the details of the attack in a few slides' time. I think it's still quite pertinent today. So I'll explain to you how it works. But basically, it was exploiting a capability, this fragmented delivery, which was missing from the Bellari-Kono-Namprempre model, quite naturally. Okay? So they assumed that ciphertexts were always delivered atomically, a whole ciphertext in one go from the sender to the receiver. Whereas in reality, because the protocol is running over TCP/IP, the attacker can dribble, he can feed small amounts of ciphertext at a time and observe the reaction of the server, for example. So back in 2008, 2009, OpenSSH released a patch to stop this specific attack. And I will explain a little bit later on what their patch was. It seemed to be effective at the time. So that was 2009. Then in 2010, working with Gavin Watson, I analyzed SSH CTR, which is the counter mode encryption, and it already had a security proof from Bellari, Kono, and Namprempre, but what we just showed is that there was something wrong with their model. Their model wasn't really broad enough. So we proved SSH CTR secure in an extended security model that captured this capability of the adversary to deliver one byte or a few bytes of ciphertext at a time. But this was very much a bespoke security model that we developed specifically for SSH CTR and not really capable of more general application. So then, like all good researchers, you keep going and you develop your ideas and your models. So then in 2012, we published a follow-up paper. This was a Eurocrypt 12, which looked more generally at this question of ciphertext fragmentation. How can we model that? More generally, what can we construct schemes? What can we do? And we also formally modeled this idea of hiding the boundaries between ciphertexts. Remember I said that SSH is trying to make a long sequence of ciphertext and MAC values just look like a pseudorandom stream. So in this paper, we also introduced boundary hiding security notions, which capture that, formalize that idea of security. And also we introduced a special kind of denial of service attack model, because one of the funny things about the existing SSH constructions is that an attacker who flips a single bit in a ciphertext, carefully chosen, can cause the SSH connection to completely hang until something like 256 megabytes of data has been delivered from the client to the server by flipping a single bit. Okay? Maybe you can already see how that would be possible. Let's go back here. Imagine this was counter mode encryption to make the ciphertext. If I flip a single bit corresponding to the packet length field, say in the most significant bit of the packet length field, I can make the receiver think, after decryption, that the packet length field is absolutely enormous. Right? The biggest possible value, it could be, well, this is a 4-byte field, so we could, by flipping a bit, make a value of the packet length field that was equal to 2 to the 31. Okay? By setting the most significant bit. By flipping the most significant bit here, we'd be flipping presumably a 0 here to a 1. Question.
Won't the MAC verification detect this?
Yes, of course. Eventually.
The MAC comes
At the end. Where is the MAC? The MAC is at the end, and the MAC is on the plaintext. So I cannot verify the MAC until I've done all of that decryption, I've received all of that data, and now I say, oh, here comes my MAC. Now I'm ready to verify my MAC. Okay? So that's what I mean by making a connection hang for a long, long time. Is it clear to everybody? And we'd like to design protocols that do not have that property, but a single bit flip enables somebody to force a connection to wait for a long, long time. Okay? Is the question here?
Yeah, if you use an authenticated encryption on an algorithm, then that problem is solved.
If you use
an authenticated encryption on an algorithm?
No, because imagine you did authenticated encryption. Okay, what's your favorite authenticated encryption scheme? GCM, I guess. No? Are you on some Caesar candidate maybe as an author?
No.
Let's think about GCM, just for fun, okay? So that basically uses counter mode followed by a universal hash function based MAC on the end, okay? And actually the MAC appears at the end. And now the MAC is calculated over the ciphertext, actually, in GCM, right? It's counter mode followed by a MAC computation on counter mode ciphertext by blocks, basically. I can just do the same thing. I can flip a bit down here, turn the packet length field into something enormous, and the implementation now waits, because it's this field that dictates how long do you wait until you think you've got enough data that you've reached the end of the packet. And there's nothing you can do to detect that until the MAC arrives. And of course, then the MAC will fail, and the connection is broken. But I made you wait 6 days, right, for all your data to arrive. Does it make sense?
Mm-hmm.
So authenticated encryption is good, but it's not the answer. It's not the full answer to this kind of attack scenario. Okay, great. Let's go forwards. Okay, so what I claim is that both of these boundary hiding and this denial of service attack problem are somehow connected to this ciphertext fragmentation and also this design choice of encrypting the length field. And I think I showed you with the denial of service attack how the length field comes into play. And actually, the encrypted length field is also the cause of the 2009 attack, as I'll show you in a few slides now.
But even if it wasn't encrypted, you could flip it, right?
That's true. That's true. So even if it wasn't encrypted, you could flip it. So imagine you had an explicit length field at the front here, you could flip it. But what you could do then, perhaps, is like add a separate MAC to the packet length field or something and check that as soon as the packet length field has arrived. They didn't do that. They didn't. Yeah. So there are all kinds of attacks here that you can play with. So you're right. Maybe it's better to say that the boundary hiding property is to do with the packet. It explains why the packet length field is encrypted, but it doesn't. The denial of service thing is maybe to do with how you're forced to process data as it arrives in kind of an online manner. You're right. It's different from the encryption stuff. Okay, good. So that was 2012. So then nothing happened for a while. And we have this thing in the UK where we're now required every 6 or 7 years to demonstrate the impact of our research on the real world. And this is going to happen next in 2019 in the UK. And my university started to put pressure on its academics early. We're a very conservative institution which likes to panic its academics into action. So we decided it would be a good idea to try to figure out, well, did anything change as a consequence of the analysis that we did back in 2009? What is the current landscape of SSH like? Okay, so we decided to do an SSH measurement study so that we could demonstrate that we had changed the internet. Right? That's the kind of thing that we have to tell our funding agencies. Right?
You switch it off. Yeah. You flip a lot of bits everywhere, right?
Yeah.
Switch off all the SSH.
Exactly. Good. So in this paper, HP16, so this is with Martin Albrecht, Jean-Paul de Gabrielli, and Torben Hansen. It was at CCS this year. We did a measurement study of SSH deployment. And we used these wonderful tools, ZMAP and zgrab, which are developed by researchers at University of Michigan, to enable us to do complete IPv4 address scans. Have any of you played around with ZMAP? Or, no, a little bit? If you do decide to use ZMAP, talk to your university network administrators first, okay? Because if you just fire it up and switch it on, it will consume all of the network bandwidth in your entire university, even at KU Leuven. Okay, so be careful. What we did then was we scanned the whole address space, so all 232 IP addresses, We grabbed the banners of all the servers we could find and their preferred algorithms. So we basically started the SSH handshake to find out what would these servers like to use, what would they like, what kind of crypto would they like to use. We found about 16 million servers in each of the scans that we did. So that means something responding on the appropriate port. What's the port for SSH? I can't remember actually. 22, thank you. Yeah. Obviously I didn't do these scans. Not my contribution to the project. So about 16 million. And we did a little bit of light Nmap fingerprinting to try to find out what are these things. They're not all SSH servers that system administrators want to remotely log into. A lot of them are things like embedded routers or firewalls or set-top boxes, that kind of thing. Okay? We didn't do much Nmap fingerprinting because it's slightly dubious to do that. But we got a flavor of what was out there. So this, I would argue, is completely different from the situation in 2009, where all this kind of embedded system stuff wasn't so prevalent on the internet as it is today, right? There weren't so many internet-enabled photocopiers in 2009. Things have changed quite a lot. So here's what we found. I don't know if you can see this from the back. Is it visible? Good. So this is just the version numbers that we found. Okay, and of course some servers lie about which version they're using. This is based on kind of standard strings that they return. You've got the first scan and the second scan. And what you notice is something quite interesting, I think. Almost everything, more than 95%, is either OpenSSH, good, we know and love OpenSSH, or this thing called DropBear. Anybody here know DropBear? Yeah, okay. I had never heard of it before we started this work. Do you know what a DropBear is? The guys who know the DropBear software.
It's an embedded SSH server.
Yeah, but do you know what it really is? In Australian mythology, it's a particularly vicious kind of koala bear, I kid you not, that drops out of the trees and attacks you. That's what a DropBear is. And that gives you a clue as to the origin of the DropBear software. This is developed by a guy in Australia. It's actually really, really interesting because it's a one-man operation, as far as I can tell, developing the DropBear software.
Wow.
There's no kind of 5 or 6 core developers like OpenSSH has or like OpenSSL would have. It's one guy doing a pretty good job, I must say, but one guy. And actually, if you look at the statistics and add up all the DropBear, it's something like 56 to 58% of all TLS, of all SSH servers now are running this DropBear software. And it's particularly popular in embedded systems and real-time operating systems and that kind of thing. So that's where it is. What's interesting, actually, is that 886,000 of them prefer, are older than version 0.52. And the significance of that is that up until version 0.52, the only encryption mode possible in DropBear was CBC mode, which meant that, if you look carefully at the code and how they do various checks, it meant that 886,000 of those servers are vulnerable to the 2009 attack, or a slight tweak of that attack. Okay, so you've got getting on for 1 million devices out there that, in principle, you can do this plain text recovery attack from 2009 against.
The older version is probably smaller.
Less code.
Yes.
Or people just don't update their versions. Who knows? Yeah. Good. Okay. Yes.
Do you know what happened between December and January? Because there's like 1 million more DropBear clients.
Yeah, I don't think
Christmas happened.
Yeah. People unwrap their Christmas, their PlayStations, their Xboxes. I don't honestly know, but what we think actually is that I think it was Comcast. What we noticed is that in the first scan there was a gigantic number of IP addresses in the Comcast IP address range. In the second scan, most of those had disappeared. So it looked like maybe Comcast, as an internet provider, had started to turn off the SSH functionality on all of their users' routers, home routers or something. But we're really not sure. We would love to know, but it's hard to tell. Actually, it would be interesting to do these scans again now, so that's almost a year ago, actually. That's January 2016, and see if things have changed again. Yeah, that's good. So there's a lot of, what you can see here, there's quite a lot of churn between the two scans, absolutely. Okay, what about OpenSSH? Well, there's a tremendous variety of versions of OpenSSH out there. Between 37 and 39% of all servers are running OpenSSH. And we actually found 166,000 of them that are older than version 5.2, and that's where the patch against our attack from 2009 was put in place. Older than version 5.2 and still prefers CPC mode. So that means 166,000 of them are vulnerable to that 2009 attack. So in terms of impact, we're probably not having very much impact. Right? There's still this huge deployed base of stuff that's vulnerable to the old attack, which was a plain text recovery attack. Okay, we'll see the details of it eventually, soon. I promise you, soon. Okay, so much for versions. Okay, what about preferred algorithms? So this is us actually starting the handshake and seeing what the server proposes as its preferred algorithm. So this is for OpenSSH. And you see the most popular thing, 57%, is counter mode of AES. Hello, you made it.
Hi.
Nice to see you. There's a chair here. You can. Fantastic. So 57, 58% of it is using counter mode with MD5 in HMAC. That's actually not so bad. It's not great, but it's not so bad. And then the next most popular thing is this thing here called ASCTR plus HMAC MD5 ETM. And ETM at is actually short for etm@openssh.com. And we had no idea what this was. And we looked for documentation. There's no RFC. There's no spec. The only documentation is the OpenSSH source code. Okay, and what happened is that in, let's think now, I don't remember the exact version number, it's 6 point something, they decided to introduce a generic encrypt then MAC construction. Instead of encrypt and MAC, do the encryption and then calculate the MAC over the ciphertext, like GCM would do, for example. Okay? Because that's a proper authenticated encryption scheme, right? And Bolari and Namprapri proved that it's in CCA, blah, blah, blah. This is a good choice, right? Kind of interesting then that 2 million servers have selected it without there ever being any kind of RFC or public discussion or whatever. It's just something that the OpenSSH team decided to add. Here's Cha-Cha Poly. This is, maybe know the Cha-Cha algorithm. It's an algorithm, a stream cipher designed by Dan Bernstein. Poly 1305 is a MAC designed by Dan Bernstein. So this is DJB crypto creeping into OpenSSH. There's nothing wrong with that. It's good crypto. I've tried to break it. Only at 1.7% at the moment, but it became the default algorithm in OpenSSH 6.9. And we're now at 7.3 or 7.4. So you would expect over time that Cha-Cha Poly will rise up. Okay? But it will take a long time because, as you saw from the statistics back here, the most popular version of OpenSSH is still 5.3 with 2 million servers. And that dates from 2010, 2011, something like that. So it's very slow for the population to change over and to update. Okay? And this is largely determined by, I think, what the major Linux distros are doing, what they're choosing as their default version to include in their packages. Okay. Another thing to notice, actually it's not on this slide, we found something like 150 different algorithms in use in OpenSSH as the preferred cipher of at least one server. 150 different combinations. And you might see where those start to arise because you can have AES with counter mode, or with 1 to 8-bit keys. You can have AES with 256-bit keys. You can have HMAC based on SHA-2 or SHA-1 or NV5. You can have this encrypt and MAC thing. You can go all cool and modern and have Cha-Cha 20 Poly 1305. If you don't care about security, you can have DES with HMAC NV5, 40,000 servers. Okay, that really is DES, right? 56-bit keys. Yeah. It would be funny if it wasn't so sad. Okay, so, and that's really where the title of the paper comes from, right? There's a lot of different crypto being used as the default algorithms. Of course, the actual algorithm that you use in any given SSH connection is determined by the client and the server talking to each other. So it might be that if people are using modern clients, they would never select DES. I don't know. We don't have access to that kind of data to tell us what algorithms are actually in use on the internet. We just know what servers prefer to use. If we now come to look at DropBear and its preferred algorithms, there's much, much less diversity. It's much more kind of vanilla, old school, quite boring crypto. For example, the most popular thing is AES in counter mode with HMAC SHA-1 truncated to 96 bits. Okay, it's mostly counter mode, a little bit of CBC still, so if you add up these two together, you get something like 8%. And actually, that 8% is vulnerable to a variant of our attack, as I mentioned, from the 2009 paper. So there's nothing really exotic here. And in a sense, that's a good thing, because this is a one-man operation, remember? And so perhaps if he had added more crypto, there was more chance of it going wrong. Right? I mean, we can maybe debate that after the lecture, whether more crypto is a good thing or more crypto is likely to lead to more attacks. I'm sure you all have your opinions on that. Okay, so that was the state of the landscape. We thought, well, okay, that's interesting. Let's start thinking about what we can say about the security of all of these different crypto options that are out there. And to be honest with you all, ever since 2009, 2010, the patch that they had applied in OpenSSH for CBC mode had bugged me. It didn't feel right to me. So we decided to go back and take another look at it, and we found a new attack. That's the sort of the headline. So here's the picture again of the thing that we're studying. It's encrypt and MAC construction, Ingrid.
Okay.
Maybe you'd like to talk us through? No, I'm joking. If you come late to my lectures, you get given a hard time. Even if you're a professor. Sorry, I've blown my chance of ever getting a job at KU. Okay, so now let's ask the question of the audience. How are you going to do decryption of a stream of ciphertext bytes? So some bytes start arriving in some buffer that you're building. What are you going to do? And we did touch on this a little bit already, and we were discussing the bit flipping stuff, right? So what would you do first? As a programmer, you have to implement the decryption algorithm for this construction. So all the programmers in the audience.
You need to decrypt the first packet because you need to get the length out.
Decrypt the first chunk.
Yeah, the first block.
The first block. So let's think we're doing CBC mode here. Those 4 bytes are always going to be in the first block. Otherwise, you're using a tremendously bad block cipher, right? With only 4 byte blocks or something like that. Less than 4 byte blocks. Okay? So think AES, the block would be 16 bytes. So the first thing you would do is you'd say, okay, I've got my first block. Let me decrypt that, and now what? What do you do next?
Then once you have the length, you just go until the length.
So you would keep accepting data and maybe decrypting it as you go along because you can?
Yeah.
Okay, good. What would you do next?
Verify the MAC.
Yeah. And what would you do if the MAC fails?
Throw everything away and give it failure.
You would maybe, what would you do with the connection?
I would keep it open actually, I would think.
Also you retransmit?
You might retransmit. There might be something that you do. There might be some behavior that you do that gives away to somebody having a happy.
Well, you are using CBC, no?
Yeah.
So that's CBC MAC.
No. The MAC is
just
something
encrypt.
like, think of it as HMAC. It's completely separate, has a different key from the encryption algorithm.
And how do you do the padding verification? I mean, how do you?
That's a good question. All you do is you look at this byte here,
Okay.
and that tells you how many bytes you should remove.
So payload is always a multiple of the block length.
Yes, exactly. That's one of the requirements. So actually, the length field here is not completely unrestricted in what values it can take, right? Because after you've done your padding and so on, this length field is going to be a multiple of the block size, more or less. In fact, not quite, because what the packet length field measures is the length from here to here, so it has to equal -4 modulo the block length, right? Because you subtract the 4 bytes for the actual packet length field. So it's not completely free. Okay, so back to your software that you've just written. Okay, congratulations. You've just built an insecure decryption algorithm. Now, can anybody see why? So the trick is this. We took the content of the first block and we said, okay, let's call the first 4 bytes of that our length field, and now let's keep decrypting until we reach what we think should be the MAC tag, and now let's verify the MAC, and if the MAC is wrong, let's send an error message or tear down the TCP connection or whatever, something that we can see. Okay? Now, the point about that is that for an attacker, he could send any block here as the first block, in particular any target block from the stream of ciphertext blocks. And its content will be interpreted as the packet length field. And then the number of bytes that you need to send in here to trigger the MAC verification and then the MAC failure will tell you what was in the packet length field. Okay? So that way, you can easily learn 4 bytes of the first block of data that you put, the 4 bytes of the plain text block corresponding to the ciphertext block that you put here. Okay? And this is basically exploiting this kind of cut and paste property that CBC mode has, that you can move blocks around, and somehow the decryption of a block in some position is meaningfully related to its decryption in some other position, right? Because of the way the equations are set up. I'll show you what I mean in the next slide. Okay? So here we go. Here's the idea. So what I will do is I will put here a target ciphertext block as the first block of the ciphertext at the beginning of a packet. It will be decrypted using whatever the IV should be. It's maybe the last ciphertext block from the previous packet, or it's maybe some random value. We certainly know what this block is. And that will give us a length field down here. Okay? What I'm saying is that this will leak. The content of this will leak because that's the number of bytes required to trigger the MAC failure from the attacker's perspective. So what the attacker does is he feeds in a few bytes at a time. He watches the connection to see what happens, and eventually, when the connection terminates, kaboom, he's learned the value of the orange bytes. What I'm saying is you can translate that, because it's CBC mode, into information about the true plaintext block, because instead of having the IV in front, it has the preceding ciphertext block in the stream, which I'm calling C star I minus 1. Okay? So you can see that you can translate from the left picture to the right picture, and actually here's the magic equation that you have to solve, right? So basically what you know is that the decryption of CI star gives you a value here, and that must equal the same value here because you've got the decryption of CI star. Okay? So now look at how that value is constructed. Well, it's this block XOR this block. So this block XOR this block must equal this block XOR this block, which is basically then specializing, looking at the first 4 bytes. That's what this equation is saying. Now you can rearrange this equation to say, okay, I can compute the green thing in terms of the orange thing and these other values. Is it clear? Who's with me still at this point? Most of you, some of you.
I have
Okay.
one question.
Yes.
So I see this,
Yeah.
but I don't see how I learn the exact value of these 4 bytes. I just learn whether the MAC verification checks out or not.
Mm-hmm.
It just says yes or no.
So when does the MAC verification get done?
At the end.
Yeah. How many bytes do I have to send so the MAC verification is done? Well, it's whatever's in this field here.
Yeah.
So I count how many bytes does it take until the MAC verification is done. I observe the network each time looking for the session to be terminated, and that tells me exactly when that was done, which tells me what was in the orange, from which I can recover what was in the green. Yes?
So is it the case that instead of flipping a bit, what you do is that you put up something you want to decrypt in there?
Exactly.
Okay.
So this is the target block that I would like to get decrypted. So as an attacker, I can make this any block at all, and I'm guessing that's where your password is. So what this attack would give me is 4 bytes of your password. Okay? I'd like to be able to learn more, but I don't know how to. Right? This is the only thing I can do, at least that we could think of to do back in 2009, was to learn the first 4 bytes corresponding to the length. But learning half of your password is not bad. Maybe I can then guess the other half. What's your password? See if it's guessable. No, that won't work. That won't work.
It's shorter.
Yeah. 3 bytes. Any other questions about this attack? Okay. The guy who asked about authenticated encryption. Okay, imagine you had used, I don't know, CBC mode followed by HMAC in an encrypt then MAC construction. That's a perfectly good authenticated encryption scheme. It would still be vulnerable to this attack. Yeah? So authenticated encryption in general is not the answer here. Something else is going on. Yeah?
But this is because you release unverified plaintext. Just instead of releasing it to the user, you release it to the algorithm. Right? You
Absolutely.
use something without verifying.
Absolutely, absolutely, precisely. And it's what we called in our work plaintext dependent decryption, right? Because the decryption process depends on something. If I can find the picture again, oh, we have to go all the way back. It depends on something that was in the plaintext that, you're right, has not been, its authenticity has not been verified yet before we start using it. Exactly. So, sorry, let me not give you the impression that I think this attack is clever. It's a trivial attack, right? But the specification for SSH was published in 1999. It took 10 years were some idiot cryptographers to come along and look at this and realize that it was broken. Okay? So actually, collectively, we're doing a terrible job here. Okay? Because this is trivial, right? And yet it leads to a serious attack against the protocol, and nobody spotted it. Okay? So I challenge you to stop thinking about how can I achieve some stronger notion of security for authenticated encryption, and instead look at the real world. Because we're not winning out in the real world. Okay, here endeth the religious lecture. Okay, enough of that. Let's move on. Okay, good. So unfortunately, in the real world, things are not that simple. So this attack that I described doesn't quite work. What you actually do is you check the length field immediately after you decrypt it. So you do a sanity check. So the length field cannot be too big and it cannot be too small. It's a 32-bit field, so the maximum size of the length field, instead of 2 to the 18, could be as large as 2 to the 32 minus 1. But the spec says that you should check that the length field is sensible, without saying what sensible means, and this is what OpenSSH does. And then you also check that the length field has the right kind of modularity related to the block length, which somebody was pointing out before, okay? So you check that if you added 4 to the length field, that's those 4 bytes for the length field, and then check that modulo the block length, you should get 0. Okay? So these checks are done first before you proceed to receive other bytes. But actually what we noticed back in 2009 was these 2 checks gave you different error messages. Okay? So they actually leak information right away without injecting all the other bytes. And then if these checks pass, OpenSSH will wait for more data and then verify the MAC, and then you get a third type of error at the end. Okay, so you can break it all which ways. The problem is, as an attacker, when you inject your block at the beginning, these length checks might fail or they might pass. You only learn all 32 bits if they both pass. Okay, so you end up with an attack that recovers 32 bits of plaintext with probability only 2 to the minus 18. Okay, so the attack isn't quite as powerful as I suggested it was. But still, it's an interesting, an interesting amount of plaintext to get back, half of somebody's password.
And otherwise the connection is torn down and you cannot try again.
Yeah, it will be torn down here if the length checks fail immediately. Absolutely, thank you. That already leaks a very small amount of information because you know that either this condition was not true or this condition was not true, but it's actually quite a small amount of information relative to what you'd like to get. Good. Okay, so what was the patch that they put in place back in 2009? Well, the idea is to make sure these errors don't leak anything about the length field. So the idea is this: if the length checks fail, don't send an error message right away. Wait till more bytes have arrived, and when you get to 2 to the 18, the maximum possible size, then check the MAC and send an error message. If the length checks pass, but the MAC check eventually fails, that's the other thing that could happen when you're under attack, then again, don't send an error right away because that leaks the length field. Instead, wait until 2 to the 18 bytes have arrived and then check the MAC. So in both cases, you're going to wait for 2 to the 18 bytes of ciphertext, and the attacker can no longer do this byte counting trick to see exactly what the content of the length field was. That won't work anymore.
From where? Kenny?
Sorry?
From where will these bytes come? What if
Great question. So this relates to denial of service, right? So if I can cause the length checks to fail by flipping a single bit somewhere, I can make you wait for 2 to the 18 bytes, which is 256 kilobytes, roughly speaking. Right? So where do they come from? They come from the client hopefully sending lots of data. But if that was an interactive keyboard session, that ain't going to happen. Right? So this is not good against attackers that are deliberately trying to cause denial of service. This kind of fix. But it stops that leakage that I talked about in the attack. Or does it? Stop that leakage. So here's how we broke the patch. It's again, I do not claim that this attack is deep. It's trivial. And if we had all been paying attention, any one of us could have observed this between 2009 and now. Okay, you just have to look at the source code for 5 minutes. If the length check fails, you do one MAC check on 2 to the 18 bytes at the very end. If the length checks pass, you do 2 MAC checks. One on LF bytes and the other on 2 to the 18 bytes. Can anybody here work on side channel analysis?
Why did you do the second MAC check?
Yeah.
Good question. Because, why did they do the second MAC check? If they didn't do the second MAC check, then here you would do a MAC check on LF bytes, and you could time how long that took, and that would leak some information. And the other one would be on 2 to the 18 bytes. So there would have been another attack if you'd done it the other way around. What they should have done, perhaps, is the second MAC check here should have been done on 2 to the 18 minus LF bytes. So the total amount of MAC checking is over a particular amount of data. That doesn't quite work either because of things like Lucky 13 style, very careful timing, right? There's more you can do. So anyway, let me show you first of all the attack. There's a timing attack. Let's see, let's just show you the attack. Where's it gone? Oh no, it's not even here, it's so trivial, right? There's a timing difference between these two cases. If I inject my chosen block at the beginning, and then throw 2 to the 18 bytes very, very quickly at the server, and then time how long does it take for the error message to come back, I can tell the difference between these two cases, because one of them, the MAC verification, will take longer than the other. So this is now using a flooding capability, the ability to deliver 2 to the 18 bytes quickly, and then time what's going on. And that's the opposite of the fragmented capability that we used in the previous attack. So, but they're both possible. And you know, we prototyped this, and you can see a huge timing difference. The timing difference, on average, is something like 2,000 times bigger than the timing difference that we used in the Lucky 13 attack on TLS. And that we could measure remotely over a network, just about. So 2,000 times bigger, yeah, it's a walk in the park by comparison. Okay, so that patch didn't really work. We told the OpenSSH people about it in May, and they fixed it in OpenSSH 7.3, which was released a little bit later in August. And there's a bit of a gap here. They didn't do any kind of emergency fix. And from their perspective, I think it's quite defensible because the attack is sort of low probability, it's quite hard to do. But they've actually also been trying to get rid of all these old algorithms for years now. Like they've deprecated CBC mode in OpenSSH. And you know, the default is now cha-cha poly. So then, okay, so what about the rest, right? As we saw in our survey, there's this kind of diverse range of possible encryption algorithms out there. The third part of our paper was to analyze some of these. Not all of them, but some of them. So let me skip this. This is basically saying why you can hope that counter mode might be secure, okay? Because this chopping of blocks thing doesn't work anymore. You can't move blocks around like you can in CDC. So if we look at OpenSSH and what's been going on there, they introduced a number of different schemes over the years. So they, first of all, AES GCM. And they learned something. They learned that you shouldn't encrypt your length field. It's dangerous. So the length field here in this construction is now associated data instead of plain text that gets encrypted. What that means is they're giving up on the length hiding property to get some other kind of security. So they're abandoning the prevention of traffic analysis. Yes?
Why not have just sort of integrity check on the length and then you're good?
That would have been another possibility. I think the general issue is that they don't want to change the packet format too much. So there's like kind of backwards compatibility issues that come into play as well. But I agree with you, that would have been a very natural and simple solution. Okay. Then there's generic encrypt NMAC, which I mentioned before. Here the length field is not encrypted anymore, but it's protected by the MAC. So they build an AEAD scheme with the length field being part of the associated data. Okay, so again, no encrypted length field anymore. And then with ChaCha 20 Poly 1305, they reintroduce encryption of the length field. Okay, so they clearly care about encrypting the length field and trying to prevent these kinds of traffic analysis attacks, because they worked quite hard in ChaCha 20 Poly 1305 to bring it back in again. Is it secure? Well, good, it is actually. As long as the basic building blocks are secure. I mean, I don't know, is ChaCha 20 a good stream cipher? Probably yes. Okay, so here's what ChaCha 20 Poly 1305 does. Yeah, you have to squint at this a little bit. We've got the same basic packet format as before. We actually have two separate instances of ChaCha 20 with two separate keys, K1 and K2. And what we do is we encrypt the packet length field using K1, and everything else is encrypted using K2. Okay? And that means that somehow there can't be any bad interactions between the kind of encrypted blocks in the two parts. You can't cut and paste from over here to down there. But actually that's complete overkill, it's not necessary, because you're basically using kind of the ChaCha 20 PRF in a kind of counter mode, and then these cut and paste things don't work anymore anyway. Okay, so they over-designed it in some sense, and they end up with a 512-bit key, 2 times 256 bits, which is kind of crazy and not necessary. You also use K2 to derive the key for the poly 1305 algorithm, and these instances are separated from each other by careful use of sequence numbers and block numbers. Okay, so you've always got diverse inputs to the Cha-Cha-20 algorithm for each of the calls that you're making. So everything is properly separated. Yeah, that's what that thing is highlighting now. So now what we've got actually is an encrypt then MAC construction, with the encryption being based on 2 instances of the Cha-Cha-20 stream cipher, and the MACing, the integrity protection, being provided by this poly 1305 MAC algorithm, which is a very fast, efficient, and actually information theoretically secure universal hash function. So it's a security proofs for this construction, at least in normal AE models, are really quite straightforward. Okay, I'm out of time almost. Let me just say what we proved. We used the security model from our old paper. This is this thing, remember, that allows you to do this fragmented delivery of ciphertexts to prove the security of these different schemes. Actually, we found out that our models were wrong. So this highlights the fact that these models are now getting very complicated for humans of limited intelligence to understand. I include myself in that. They're really quite tough to understand. We also introduced an integrity notion because that was missing from the 2012 paper. And then what we prove is that all of these different schemes are secure. But we found another bug, actually. When we looked at this generic encrypt and MAC construction, it was retrofitted into the legacy encrypt and MAC code. And what that meant is that if you think about encrypt and MAC, the MAC is only computed on the plaintext. So if you want to compare your computed MAC to your received MAC, you have to wait until you have the plaintext. And they wanted to reuse that little snippet of code in their encrypt and MAC construction, where now the MAC is on the ciphertext. So what they do in their code is they were computing the MAC on the ciphertext, storing the MAC value, doing the decryption, and then comparing the computed MAC value to the stored MAC value. Or computed MAC value, sorry, to the received MAC value. In other words, the actual MAC check wasn't done until after the decryption had been performed. Which, if you think about it, is completely crazy, right? The whole point of encrypt then MAC is the MAC is computed on the ciphertext. And then you reject immediately if the MAC is wrong in the ciphertext. And that's what stops active attacks against bit-flipping attackers or whatever, people like me, right? We didn't find a concrete attack of it based on this, but there could have been. For example, if they had used CDC mode with that had some kind of padding oracle in it, then the fact that the MAC was not actually checked until after decryption would have enabled a padding oracle attack. Okay? That didn't happen. They got lucky. And now it's been patched. But I think this illustrates the real danger of adding more and more stuff on top of existing code and hoping that it all kind of works together. Sometimes it doesn't. Okay, I think I'm out of time, so I'll skip this slide, which basically says what did we find out about boundary hiding and this denial of service property. These are more advanced properties that you might like to achieve, and come to some conclusions. We've tried to develop a deeper understanding of this SSH encryption, particularly in OpenSSH, all the different encryption modes. We did our measurement study, which threw up some interesting results. We had the new attack on CDC mode, and we've also given a provable security analysis of the other modes in an appropriate security model, which is not the standard security model for symmetric encryption. Interestingly, none of the schemes that are currently in use has all of the security properties that you might like, particularly against active attackers. So they still have these nasty denial of service attack problems. So if we go back just 1 second to the Cha-Cha-20 picture here, you can see that if I flip a bit here, I can make the packet length field enormous. So with one single bit flip, I can cause the connection to apparently hang as far as the users of the connection are concerned. Okay, and it's possible to avoid that by, for example, macking that field at the beginning or doing something else. Okay, so none of the actual constructions in use have all of the properties that we might like, that we think the designers want to have. So what we're actually working on now is developing and prototyping efficient, provably secure schemes that do have all of those desired properties. And we're currently talking to some of the people in the OpenSSH team hoping to engage them and get them excited about even crypto beyond DGB crypto. Okay, if you're interested in reading further, here's some literature, but I've already taken up a whole hour of your time, so thank you very much for your attention, and if we've got time for questions, I'll